Hi, what I'd like to talk about today is piezoexcitation versus photothermal excitation. This is important when we're working in dynamic modes of operation, where the cantilever is oscillating during our measurement. And to start with, I've drawn in the center of the screen a typical AFM readout setup, where we have our cantilever. We have a readout light source that we shine down onto the end of the cantilever, and then that light is reflected back onto the photodetector so that we can measure the deflections of the cantilever. And if we were to look at the cantilever itself, in terms of its frequency response, in amplitude versus frequency, we'd see some kind of, in the ideal case, we'd see some kind of peak right around the resonance frequency of the cantilever. And in the phase versus frequency response, we'd see some kind of phase shift right around the resonance frequency of the cantilever. When we use piezoexcitation, we take a shaker piezo that we place right near the chip of the cantilever, and then we apply an AC voltage to this piezo so that it will expand and contract at the frequency of operation. What that does is then send acoustic energy into the cantilever through the cantilever chip, but also it sends acoustic energy out into the medium, the air or fluid that we're working in, and also sends acoustic energy into the surrounding structure. And the problem with that is then in our frequency response, we're not measuring just the cantilever response, but we measure the response of everything together. And that manifests itself as what's known as the forest of peaks, where we have not just a nice clean peak in the ideal case, but we have a bunch of other peaks in our amplitude versus frequency response. It can be something kind of nasty like that. And then each of those peaks would also have a phase shift associated with it. We'd have a phase that would wrap around and around from each of these frequencies, or each of these resonant peaks. And so for a user, it becomes quite difficult to know, first of all, which frequency is a good frequency to operate at. It could be this one here that is close to what the cantilever should display, but it could also be this frequency here that's a bit off of the cantilever ideal resonance frequency. So that's one challenge. And the second one is that because it's a combined response of not just the cantilever, but also the medium and the structure, it's quite sensitive to changes in things like the amount of fluid that's there or the temperature of the fluid. And so as an experiment goes on, and say the fluid evaporates, if we're working in liquid, then these peaks can change quite drastically in size, which makes it not a very stable way of exciting the cantilever. In contrast to piezoexcitation, we have something called photothermal excitation. What we need for that is not a shaker piezo, but a second light source that I'll put here called a photothermal light source. And also we need an optical filter that we place in front of the photodetector. And what we do with this light source is we shine it also onto the cantilever, but not at the end of the cantilever. Like we do for a readout light source, we typically shine it down onto the base of the cantilever. And so it will go down onto the cantilever and get reflected back and blocked by the bandpass filter here, so that the light at the photodetector is only measuring the readout light source and not the photothermal light source. And what happens is that if we look at the cantilever, as we shine this light source onto the cantilever, we heat up the cantilever. And the cantilever will have a coating layer and a base layer, and those two might expand at different amounts depending upon their temperature coefficient of thermal expansion. So typically the coating will expand more than the base, and so we'll start to deflect the cantilever as we heat up the cantilever because of this light source. And so if we modulate the intensity of this light source at the frequency of operation, then we'll start to drive an oscillation of the cantilever because of the heating from this light, the alternative heating and cooling of the light at the frequency of operation. And the really nice thing about this is that it's a very, very local phenomenon. We're just heating the cantilever, and so we just see the response of the cantilever, not of the surrounding medium, not of the surrounding structure. And so then what we recover is in our amplitude versus frequency plot, not this forest of peaks, but something that looks much closer to the ideal response of the cantilever, both in amplitude and phase. And so the nice thing about this is, well, for the user, it becomes very, very clear which peak to operate or which frequency to operate at. You work at what you predict for your cantilever resonance frequency. And also, if you start to think about using the cantilever response in some kind of a model, that you have a response that's much closer matched to theory. So you can start to better apply theoretical models to your cantilever response in terms of your experimental setup. And finally, because it's shaking just the cantilever and not the whole surrounding structure, we're much less sensitive to changes in the amount of fluid, for instance, or the temperature of fluid, or the way that the cantilever happens to be mounted onto the shaker piezo. And so the amplitude response and the phase response become much more stable. So it can work without changing parameters quite so often for a much longer measurement. So just to summarize then, photothermal excitation is a much more clean and stable method of operation for dynamic modes, for driving the oscillation of the cantilever, and for systems that have both piezoexcitation and photothermal excitation. Photothermal becomes the preferred choice for many, many, many users.